Today we're going to be talking about simple harmonic motion, specifically mathematically analyzing the motion of an oscillating spring and weight. Now if you look in the bottom right hand corner, you can see that we have this red ball denoting our weight connected to the spring. In this scenario, we're going to be stretching the spring and releasing it, giving it some type of motion. And you can see when it oscillates up and down, it's going to trace this specific position graph, which is denoted with this either cosine wave or sine wave. Now, the way that we're going to be mapping this is with a second order differential equation. And you can see right here, this is going to be the general solution that we're going to be deriving, where omega is the radiant frequency, or the square root of the spring constant k, over the mass m, and t is of course time. Now a couple of things about waves that we're also going to be able to find from mathematically analyzing this scenario. The period, which is the distance from the top of the adjoining waves. The phase shift, which in this case is 0 because the sine wave starts at the origin. And the amplitude, which is from y equals 0 to the top of the wave. Period is going to be denoted as tau, which is equal to 2 pi over the radiant frequency omega, and frequency is equal to 1 over tau. Now, here is the general form of a wave equation, and you can see that our general solution to our differential equation kind of looks similar, except it has two trig functions that are being added together. But the amplitude, which is denoted as a here, is going to be the same as this constant c1 right here. And this b, frequency, is going to be the same thing as this radiant frequency. And this t is going to be where this x minus c, or the horizontal shift, is. Now, there are a few alternative forms that we can get this general solution in. However, we have to get in something called a phase angle, which is pretty much writing one trig function as another trig function with a horizontal shift, right? Because a cosine wave is the same thing as a sine wave that is shifted pi over 2 to the right. However, we're just going to stick with this general solution with both trig functions because it's a little easier. I'm going to now shift to a whiteboard so I can show you how we're going to derive this. Alright, so let's derive this general solution to the equation, right? So you can see behind me we have three different scenarios, right? We have an unstretched spring denoted by the distance L, and then we have an equilibrium scenario where the sum of the forces are equal to 0, where the weight has been added to the unstretched spring, and the spring has stretched a distance of s. However, the spring force acting opposite to the elongation, or upwards, and the weight force acting downwards cancel out. So we can say here that the weight force equal to mg and the spring force equal to ks are equal to each other. So we have mg is equal to ks. Alright, for this third scenario, we have this mass that has been stretched a distance calling x past the equilibrium position. So when this mass is released, we're going to have some type of motion or oscillation that goes up and down. So no longer are the sum of the forces equal to 0, the sum of the forces are equal to mass times acceleration. So first thing we're going to do is look at the equilibrium scenario, right? So we have said that mg is equal to ks. So what we're going to do is subtract over the ks, where we have mg minus ks is equal to 0. Okay, so this is important, and we're going to remember this and kind of put it to the side for the time being, and we're going to move on to the dynamic scenario, which we're really interested in. Okay, so summing all the forces in the body, we're going to have mg minus your spring constant k times the distance that the spring has been stretched. So the spring has been stretched a distance of s plus x. In the static scenario, it has just been stretched a distance of s, but we've added on this x distance right there. So we're just going to put this s plus x here, and that is going to be equal to mass times acceleration. Now I know it doesn't look like we have any differential equations going on yet, and you're right, but we're going to change that right now, right? So we have some function x of t relating to the position of the oscillating spring. The derivative of that position is going to be velocity, and the second derivative of the position is going to be equal to the acceleration. So what we're going to do is substitute this second derivative into the acceleration right there. So let's go ahead and do that. We have mg minus k times s plus x equal to m times that second derivative. Okay, so we're almost to the point where we can start solving our differential equation. However, we need to clean some things up, right? I'm going to distribute this spring constant into these parentheses right here. Okay, so we have that mg minus ks minus kx is equal to m times the second derivative of your position. So, looking back at our static case, we see that mg minus ks is equal to 0. So looking at our new equation, we see this mg minus ks pop back up again. So simply we can just say that this part of the equation is equal to 0. So lastly, our last form of our differential equation is going to be m is equal to negative kx. So we don't have to manipulate anything anymore with the actual physics behind it, right? So let's go ahead and just add over our spring force and try to get this into standard form, because always standard form is your best bet when solving differential equations. So let's go ahead and add this over and get this coefficient to be a 1 in front of our highest order derivative, right? So when I add this over, I'm going to have m plus kx is equal to 0. So the last thing we have to do is divide everything by m to get this coefficient to be a 1. Okay, so this is the differential equation we are going to be solving. And I'm going to flip to a new clean whiteboard where we can do this. Now let's solve this second order differential equation. The first thing we're going to do is we're going to induce some substitution, and then we're going to try to classify it and see what we can do to it. Alright, so if you remember from the beginning of the video, I said that omega, or the radiant frequency, is equal to the square root of k over m. And we're going to try to substitute this into our differential equation somewhere. It's going to yield omega squared x equal to 0. Okay, so I've squared our omega because that square cancels out a radical, leaving just this k over m, and that's what we want. Okay, so it's important to see that this is just a constant, right? Because omega is just made out of constants, and this is a constant coefficient in front of our second derivative. And this differential equation is equal to 0, and it's linear. So this is a linear homogeneous differential equation with constant coefficients. So that's great. This is actually one of the only differential equations we can solve with using algebraic means. So what I want to do to kind of show what this means is I want to look at the first order example of this differential equation to kind of show what solution we're going for. Right, so let's look at this scenario where we have x primed plus some constant times x equal to 0. This is just the first order example of this, right, where k is a constant. If I subtract this over, we have x primed is equal to negative k times x. Now negative constant is just the same thing as a constant, so we can erase that. So we're looking for a solution where the derivative is just equal to some constant times itself. And that's just an exponential function, right? So if we have x is equal to like e to the 4t, for example, the derivative is just going to be a constant times itself, right? So it just so turns out when solving a second order differential equation, the same thing kind of happens. We're looking for a solution that yields some e to the nt, where n is going to be a constant. I used n instead of k for some reason. I don't know. So what we're going to do is we're going to take the derivative of this function and we're going to plug it into this differential equation and kind of see what happens, right? We're going to try to find a solution. We're particularly looking for this n right there. So x primed is equal to n e to the nt, and x double prime is equal to n squared e to the nt, okay? So we're going to go ahead and plug these into this equation. When we have n squared e to the nt plus omega squared times e to the nt equal to 0, okay? So we're going to factor out our e to the nt, and we're going to be left with a n squared plus omega squared equal to 0. Okay, so one can notice that this is never 0, right? An exponential function can never be 0. So the only solution to this is when n squared plus omega squared is equal to 0. So like I said, we're trying to solve for this n. And something a little funky is going to happen, right? When we solve for this n, we're going to get n is equal to the square root of negative omega squared. And you can see here that we have this negative discriminant under the radical. That means we're going to have some complex thing going on under the radical, right? So n is going to be equal to some complex number where we'll say alpha is the real part of the complex number plus beta, which is the imaginary part of the complex number, times your I. Okay? So this is the imaginary part. This is the real part. Okay, so solving this, we have n is equal to plus or minus I times your omega, right? And that comes from the square root of negative 1 times the square root of alpha, square root of omega squared. Okay? And this is none other than I, and this is just omega. Okay? So we've come up with two solutions for our n, right? When solving for n and plugging this into our exponential, right, trying to get our solution, since we have two of these, we're going to have two linear independent sets of solutions, which yields our two constants and everything. Anyway, but plugging in an imaginary number into this, we are going to use Euler's identity to derive some type of general solution. However, I'm not going to show that. I haven't even got into that, deriving that part, so we're not going to do that. But we are going to get to the general solution when we have these complex conjugate roots when solving for n. And that is just x of t is equal to c1 times e to the alpha t sine of beta t plus c2 e to the alpha t cosine beta t. Okay? So this is going to be the general form of our solution when we have these complex conjugate roots. So when solving for n, okay? And we can see that this is our imaginary number. We don't have any real part, right? The only part is this beta. And this beta is just going to be our omega, right? So anywhere we see our alpha, we're just going to plug a 0 in. Anywhere we see our beta, we're going to plug our omega in, right? So by doing this, our general solution to the equation is x of t is equal to c1. I'll put the cosine first for no particular reason. Cosine of omega t plus c2 times the sine of omega t. Okay, and you can see here we have just derived the general solution to the harmonic motion that we are just trying to describe. So, hope you enjoyed. That was a little lengthier than I thought it was going to be. But anyway, thank you.